Wonderful. Thanks a lot. It's a real pleasure to be here. Actually, Fields Institute has always kind of had like a special place in my heart in many ways, because this was actually the location of the first conference that I ever went to. And first paper I ever finished up was actually literally at that desk right over there. So yeah, it's a great place, and it's great to be back. So what am I going to be talking about? Well, it's a good question, something I asked myself on the flight coming back here last night. But it looks like I'll be talking about area laws for unbounded Hamiltonians. And so what do I mean by that? Well, what I mean by that is what I want to be able to do here is talk about what the structure of ground states are for a broader class of Hamiltonians than currently has been understood. So basically, what we'd like to be able to do is understand the entanglement structure of the ground states of operators that have an unbounded structure. And why is that a problem? Well, at first glance, it doesn't seem like that should be that big of a generalization, arguing about the properties of unbounded operators. But it turns out the structure of unbounded operators is subtle. A lot of the things that you would like to believe that you can do with unbounded operators may not necessarily end up holding. Like, for example, I would often like to be able to say that I've got, an expression like e to the a for some particular operator. I'd like to be able to write this as a sum from j equals 0 to infinity of a to the j over j factorial, right? But one of the things you got to worry about is that this series the convergence of it may not make any sense if you're dealing with an operator that's unbounded. Because if you truncate this at any finite order, the thing won't make any sense. But even if it's an unbounded operator, if A is anti-Hermitian, then actually the spectrum of this is well defined. So this, for unbounded operators, you can actually end up getting differences between the spectral definition of the function and the series definition of it. And many of these subtleties end up coming up over and over again inside the proofs, and things that you would ordinarily take for granted fall apart. And so as a consequence, it turns out that some of the foundational things that we believe were true about one-dimensional Hamiltonians actually were sitting on a shaky mathematical foundation. And the point of this work was to actually seal that gap and provide a good mathematical foundation that says the things that we believe ought to be true about one-dimensional quantum systems actually will often hold in cases where the Hamiltonian has an unbounded spectrum. Of course, not always. We can always envision cases where, like, let's imagine I set A to be like the infinity matrix. Okay, well, duh, nothing makes sense then if I define it like that. But that said, things like, for example, bosonic systems, where we could have an unbounded number of photons in a particular mode. These are the kinds of things that we can now talk about coherently and discuss area laws for this. Yes?
So you mentioned non-Hermitian operators, anti-Hermitian operators, or you were referring to the exponent of A, or
yeah, I'm referring. A itself is anti-Hermitian.
Oh, then E of A is unitary, so
right.
That's
and so then, yeah, what I'm saying is the exponent is bounded. But if we're taking a look at the series definition, right, the series definition won't necessarily end up converging for all of the individual blocks. So it makes much more sense to use the spectral definition of the operator exponential in that case, rather than the series expansion, because the series expansion doesn't have a meaningful remainder term. And any argument that's arguing about the remainder term that you end up getting in these series can't be used. And this is something that stands in the way of many of the existing proof techniques that were used involving Lieb-Robinson bounds, because they depend on the norms of commutators between different things. And well, if you got the norm of a commutator between two unbounded operators, it could be as big as you want, in many cases at least. Yeah.
Just to clarify, when you say unbounded, you mean the matrix has infinite size, or the elements of the matrix are infinite?
So specifically, what I mean here is I actually mean a case where it has infinite size, and in the limit, as you end up, say, imagine you're looking at a truncation. So consider a operator that we've got over here, right? And we want to take the limit as the size of that operator goes to infinity. we could have a situation where, our spectrum ends up looking like, some slowly diverging function, like, let's say, root n over here. This would be like root n plus 1, so on and so forth. As the size of the matrix ends up increasing, then this will end up approaching an operator of infinite norm. But at any finite truncation, it would make some sense. So we're talking about the infinite limit of this type of matrix. Okay. And what we want to be able to argue is that there's some coherent and consistent way of us thinking about truncating these systems so that we can end up applying existing theorems to show that there's a one-dimensional area law. So yeah.
One more point of clarification on that. But I think about, let's say, the density matrix for a Gaussian wave package.
Right.
So that all the elements of that are finite and they decay exponentially, but it is an infinite size matrix. Is that the problem? Is that not enough there?
Yes, this is exactly the kind of mathematical hole that we wanted to be able to plug. We wanted to be able to show that simple systems like this that we know in our guts aren't actually really all that poorly behaved, do satisfy the requirements for an area law, despite the fact that they might violate the formal assumptions that are made by existing proofs. Any other questions? And please, I do want you guys to interrupt me anytime you have something. All right. So the main point, or the main thing that I'm going to be doing is I'm going to be motivating what area laws are and why they're important. Then I'm going to take you through a sketch of the proof that we end up having of the 1D area law, and then finally discuss some of the implications and actually some of the possible extensions that we could end up seeing beyond this work, or that if some of you are interested in, you could help develop. So the basic idea is of an area law. It's an area law ends up talking about what the structure of entanglement is in the ground state of a particular system. So ground state is said to obey an area law if for any cut that you end up making in the qubits, like if you imagine a bipartition of the qubits, so you put them on one, part of them on one side, part of them on the other. The question is, what's the entanglement across that bipartition that you would end up seeing? And if it has an area law, then the amount of entanglement that you end up seeing will scale like the area of the cut. We'll say that it has a volume law if it scales like the volume of the cut between the two. So in the case of 1D, right, what we have is we might have a lattice like this. So each of these would involve, in the simplest case, qubits. So they're two-dimensional vector spaces for every single one of them. And the question is, well, how much entanglement do we end up having in the ground state, i.e. quantum correlations between the left-hand and the right-hand side, if we kind of slice it about an arbitrary point in the middle? And it has an area law if, again, this amount of entanglement scales linearly with the area of this one-dimensional piece that we're cutting out. So what would be the area of this slice in a one-dimensional thing? Well, it's constant, right? It can't scale at all. So in this case, if it's got an area law, it actually has a constant amount of entanglement when between these two pieces, regardless of the size of the system. And this is really significant because what a constant amount of entanglement means is no matter how many quantum bits we end up growing on each of these two sides, the amount of correlation between the reduced density matrix that we end up seeing on this side, let's call it rho, and sigma over here, the amount of the entanglement entropy of those two systems will actually be constant as we end up increasing the size of the system. So this means they're basically weakly correlated. Yes.
Yeah. So could you clarify? You're not assuming any nearest neighbor interaction. You assuming all to all.
So at the moment, what I'm doing is I'm just discussing what's meant by an area law. Now, the cases that we end up getting from things like the Hastings-Coma proof for it will have nearest neighbor or exponentially decreasing interactions that will lead to a 1D area law. But that's an extra step down the line.
No, well, what I don't understand is if you don't assume nearest neighbor, then 1D, 2D, 3D, or ND doesn't really matter because There is no, like, you have just a group of qubits that are interacting.
Mhm.
And this one-dimensional, two-dimensional doesn't really make any sense.
Yeah, if you, it depends on how you're thinking about it. So let's take a look at the different cases that we know this ends up holding for. So the one case, there's literally only one case where we've, without loss of generality, proven that we end up having a area law, and that's for the one-dimensional Hamiltonians like this. And in particular, we need to have something like Archer is alluding to. We need to have very local interactions between the individual subsystems in order to be able to have this. So for example, one sufficient condition for this, but again, it's not necessary, but one sufficient condition to have a 1D area law would be to have these individual quantum systems over here only interact with their nearest neighbors. Systems like this that have these local interactions will always, in one dimension, have an area law. But it turns out that actually we can go one step further than this, where if we consider every qubit or every qubit more generally, because this doesn't necessarily need to just be a finite, a two-dimensional system. It could be a d-dimensional system. The whole reasoning will end up working too. If we end up having couplings that end up decreasing like a sufficiently fast power law going down from this point, specifically any power law that is faster than I believe second order, like 1/x squared, that will end up also satisfying a 1D area law. Okay.
Okay, so the dimensionality, physical dimensionality of the system comes into play through essentially the scale interaction.
Yes.
Between this.
Yes.
So when you say one-dimensional, you mean something about the, like, it has some implications about the decay.
Right.
So what are those?
So basically, well, what I'm meaning is I mean over here that this distance that we're taking a look at is the distance between the two sites in the linear graph over here. So if say I'm dealing with a case that has exponentially decreasing interaction strength, that's one case that will satisfy an area law. And so then in that case, the interaction strength for the Hamiltonian term that you're looking at, let's say I've got E distance, negative distance ij, hij. This would be a typical coupling term that we would see if we had something had exponential decrease. Here, distance ij would be the graph distance between vertices I and j in this. So if this was I and this is j, then the graph distance between here would be 2, right? And then hij would be just some coupling that describes the particular Hamiltonian that leads to an interaction between those two subsystems. So that's kind of like that's how you would end up seeing a kind of quasi-local Hamiltonian coming up over here, where we don't have nearest neighbor interactions technically, but they're sufficiently rapidly decaying that there's kind of no difference when it comes to the scaling in the end. All right. Now, this is in general, right? What ends up happening is after the 1D area law was discovered, the question was, well, does there exist a two-dimensional area law under similar circumstances? Because, it seems reasonable that if we did the exact same thing and we ended up now instead demanding that we only have Hamiltonians that end up coupling nearest neighbors on the two-dimensional lattice, say, it's reasonable that it should also be expected to satisfy an area law. In which case, for an area law here, would have entanglement entropy that scales linearly with the size of the system, not constant, because the area of a 1D cut that we end up making inside this now will have a number of sites that scales linearly as we end up increasing the size of the system, okay? Rather than a constant like you get in one dimension. So
still, like, I know it's probably obvious for you, but how do you define this entropy, like a mutual entropy, right? So you have two parts, and then
yeah,
how do you kind of characterize how much entanglement you have?
Okay, So the easiest, well, what we formally do is we compute the von Neumann entropy for the reduced density matrix in one of these two subsystems. So if I call this subsystem A and this subsystem B, this one is just used in order to create a buffer between the two for technical reasons. So what we would do is we would say that the entanglement entropy, I always forget if there's a negative sign here. I think there is, but negative trace of rho A log rho A, where rho A is going to be equal to the trace over system B of the, and I guess C, of the entire density matrix. Okay, and so that's how we end up doing it. We discard the part of it that's outside of the one of those two spaces, and then we compute the von Neumann entropy of the reduced density matrix. And then that's what we end up calling the entropy of entanglement.
And the area was essentially dependent on that.
Yeah.
On like property of the.
Yeah, on basically like the size of the lattice over here. Okay, now it's reasonable to expect that in a 2D case that we'd have an area law too. So it came kind of as to everybody's surprise that first, it actually seemed really difficult to prove because when people started going through the proofs for the 2D area law, actually it wasn't a clear generalization of the 1D area law. Then things got even more confusing when people came up with numerical examples that ended up showing actually that systems in general in 2D that do have nearest neighbor interactions don't satisfy the area law. And so for this reason, actually a complete characterization of particular interactions on D-dimensional lattices that satisfy an area law is still lacking. The 1D case is the one case where we really understand it. But in 2 dimensions, everything kind of falls apart.
Still, is there an easy definition of what 1D is?
Yes. Yes. So
Just,
yeah.
I guess you're talking about difference between 1D and 2D. And
what I'm talking about, essentially, what I'm talking about here is you can end up envisioning a graph in general, right? Or anything, right? It's a question about how this distance or the coupling strengths between the interactions is computed. And so the idea in these models is that the distance is always computed in terms of the graph distance between the two individual sites. So for example, if I had, let's say I had this as my graph, right? And then the graph distance between sites I and J would be 2 over here. Okay. So we may have long distance couplings between all of these things, but the strength of those couplings in this exponential decay model will decrease exponentially with the graph distance between those two sites. And the only difference between 1 and 2 dimensions in this case is, if imagine we had 2 cases, right? If we could have this case in 2 dimensions, or we could have this graph over here in 1 dimension. The graph distance between 1 and 4 for both of these graphs is actually different. It's 3 versus 2. So the only way that the dimensionality actually formally comes up, if you think about this abstraction, is in terms of the definition of the underlying graph that you have. In 1 dimension, all of your vertices are going to have, degree at most 2, but in 2 dimensions, you could have higher degree. You could have, depending on how you choose to coordinate it, maybe 4 or whatever. Okay. Any other questions before we proceed? Okay, and again, just going back to the point I was trying to make earlier. The key thing about states that are systems that end up obeying 1D area laws is it ends up saying the quantum state on the left is very poorly correlated with the quantum state on the right. And that is actually a really, really important property for a lot of condensed matter physics these days, because it allows you to use techniques called matrix product states in order to be able to accurately approximate these systems, because it says that if we create a bipartition between the two, there isn't very much entanglement. And you have to pay a high price using those techniques to accurately approximate the ground state of a quantum system that has a high degree of entanglement. So this over here is what justifies the performance of techniques like DMRG, which for one-dimensional systems give us ways of simulating extremely complicated correlated quantum systems because of the fact that they still exhibit one-dimensional area laws. So we can use that in order to make life simpler. But in 2 dimensions, because of the lack of a 2D area law, this is uncertain. So this is some of the justification for why it was important for us to understand the foundation of whether or not this would apply for, say, bosonic operators. Because, you know, if we have a system, not of fermions now, but of, say, one-dimensional bosons that could have an arbitrary number of bosons at each site, does everything still hold up? So to give an example of some of these cases, the first result for the 1D area laws that ended up coming out was this Hastings result from 2007. Okay, and in that case, it only ended up holding for nearest neighbor interactions, but it was quickly generalized to exponential decay as well. So the technique was based on what I called Lieb-Robinson bounds. And if you haven't seen Lieb-Robinson bounds before, they're freaking awesome. I love Lieb-Robinson bounds because Lieb-Robinson bounds, what they end up saying is that for quantum systems that have local interactions, what you generically end up getting is you end up getting correlations between different sets of qubits that obey natural light cones, just like you would see in relativity. So if you had system A over here and system B here, what these bounds end up saying is you'd have to go a period of time where the time is equal to the distance between the two divided by the effective speed of sound for the quantum system. And before that point, those two systems are uncorrelated. So it brings up actually this kind of notion of causality that you often only end up seeing in relativity, coming about just as a consequence of having local terms in your Hamiltonian. So this is something that's it's really a beautiful result. But unfortunately, it doesn't do a great job for cases that are unbounded, because as I was alluding to before, this depends on the commutators of the terms that we end up having in here. And a commutator of an unbounded operator could be and will often be an unbounded operator. And so we couldn't use that particular approach. So instead, we ended up following this approach. And you know, this is something that is actually kind of an interesting turn of events, because the original work out of this firmly came from the condensed matter theory community. Interestingly enough, all of these people, well, okay, with the exception, I think, of Landau, are hardcore computer scientists. So it was actually a very different group of people who came together and decided that they wanted a proof of the exact same thing, but one that used different ideas and avoided the use of Lieb-Robinson bounds. And instead, they came up with this notion of an approximate ground state projector in order to be able to make this proof. And from the properties of these approximate ground state projectors, they were able to end up showing that the one-dimensional area law actually ends up kind of holding in general for arbitrary systems that have finite dimensional local Hilbert space. And so what we would like to be able to do is we'd like to be able to generalize this 2017 result to hold for the unbounded case as well. And the spoiler alert, the one bummer that we end up getting from the whole thing is that, well, the 2017 result ends up working for degenerate ground spaces, it actually doesn't work in our case for the degenerate case. But I'll get to that later. So any questions about the history of this stuff or anything else? Yeah, Arthur.
I'm a little bit confused about this separation of bosons and fermions. Fermions could be from 2D lattice, bosons could be on 2D lattice. Like, why do you make the distinction?
Well, it's just because of the dimension of the local Hilbert space that we have in both of those cases. For the fermionic case in second quantization, we can only end up having, at most one fermion at each of the sites, assuming it's only one spin species, right?
I see, so it's the dimension of unboundedness versus.
Yeah, exactly. And that's what ends up making it conceptually much harder to make the similar claim about the bosonic case, whereas the fermionic case directly follows from both of these results over here. It's the unbounded local Hilbert space dimension that makes those arguments fall apart for bosons.
For bounded operators, the 2D case already worked out, right?
For bounded operators, the 2D case is anti-worked out. In that we've got counterexamples showing that the hypothesis isn't true for 2 dimensions, that there are 2-dimensional systems that have local interactions, but nonetheless do not have area laws. And so this is still a major open question. Can we come up with a necessary and sufficient criteria for 2-dimensional systems having area laws? And at present, no such understanding exists.
Great. And for 1D case, then unbounded operators, is there area law?
Yes, there is now.
Okay, and now you're looking for 2D unbounded.
Well, we'd love to show that. That's one of the things that we're talking about at the moment. But, again, we'd have to look at very restricted cases of 2-dimensional systems, because even in the bounded case, there are counterexamples where bounded operators that have local interactions do not satisfy area laws in 2D.
So then your task is to find the cases where it doesn't for unbounded operators in 2D.
Well, that would be follow-up work. We just did the 1D case here.
Okay.
Yeah. Okay, cool. Any other questions? Wonderful. All right, so let me show you an example that I love for this. And this is in part because of the fact that this is an example that I've been spending a lot of time thinking about because of simulations, because I do a lot of work on quantum simulation of lattice gauge theories. And so this is an example of the Schwinger model, which ends up modeling a 1-dimensional quantum electrodynamics. And basically, the way that it ends up working is it's actually a pretty simple model. What we have is we have a series of fermionic sites in this model at different points. And every even, or every in this case, every odd site over here corresponds to an electronic orbital, and every even one corresponds to a positronic state. And in between each of these, we end up having a electric field, essentially. And the system is set up in such a way so that it has to obey Gauss's law. So the amount of electric flux that we end up seeing given by the field has to be directly proportional to the amount of charge that's enclosed inside this 1-dimensional Gaussian surface, which would just be these 2 lines, in this case, say. Okay. And so that's how these systems end up working. And the way the Hamiltonian ends up going is that we've got 2 components to it. We have this electric field component over here. We have a mass part, which puts in an energy penalty for the mass of the electrons or positrons at each of the individual site. And then we have this hopping turn that allows the electrons or positrons to move, but they have to move in such a way that ends up obeying Gauss's law. So if they move in an appropriate way, they have to update the fields nearby in order to be able to make sure Gauss's law is satisfied. And so that's essentially how the model ends up working at a high level. Now, the thing that is problematic about it is exactly this bosonic issue that I was mentioning. So the electric field that we're looking at for each of these sites formally could be infinite. There is no cutoff that's given in nature for the maximum value that we should be setting for these sites. So the question is then, the first kind of primitive question that we would like to ask is, do these systems obey 1-dimensional area laws? Because if they do, then we can use techniques like DMRG to be able to simulate it. If they don't, well, maybe you still could use it, but you wouldn't have any rigorous guarantees at least. Okay? So that's the kind of system that we would like to really be able to understand whether there's a 1-dimensional area law for. And yeah, in each of these cases, we're keeping track of the presence or absence of an electron in each of these sites. So all of these sites are just binary variables or bits. So each of them is just a qubit effectively that will store whether or not there's an electron or positron absent. These over here have to be an entire like register that will keep track of the current electric field that we need in order to make everything consistent with Gauss's law. All right, so that's a canonical example that we'd like to do. And high level, what the strategy is that we'd like to be able to show that we can end up applying a local truncation to each of these spaces. And when we apply a local truncation, we need to show that things don't go off the rails. So the idea basically is that we're now talking about the stage that actually many field theorists just do by fiat. Often what they'll do is when they're talking about doing a lattice simulation of these systems, they'll end up imposing a arbitrary cutoff on the system. We'd like to understand, well, is that justified? You know, and even though the system with the cutoff satisfies an area law, it's not clear that the system without the cutoff does too. So we need to our task is to not just make the cutoffs, but also show that there exists this bridge between the ground states of the uncutoffed version and the cutoffed version. All right. So that's the idea behind it. And basically, there's some definitions that we kind of need to get out of the way in order to deal with this. So first thing, what we need to do is we need to construct a projector onto all of the eigenstates that correspond to a set of eigenvalues. And we'll just refer to that as a pi s over here. And basically, what we want to do is we want to be able to say that we need to talk about the truncated local Hilbert space dimension of a site. And so in essence, all that really is the rank of the projector onto the truncated subspace that we're looking at here. Okay, so that's what we end up meaning by the local Hilbert space dimension. We just mean this like the number of variables inside this particular range here. And we're leaving it general like this because we don't know the spacing is necessarily 1 between all of these guys. And so that's why we've used this kind of more complicated notation for it. But it's basically just counting what the local Hilbert space dimension is going up to a particular cutoff of lambda. All right. And then basically the next concept that we need in order to talk about this is we need to talk about kind of the truncated norm of the Hamiltonian. So when we're looking at our remainder bounds that we end up having to describe our error from this rounding procedure to the lambda, negative lambda range, we need to have some notion of the norm of the operator inside that truncated space. And so then that we use this notation over here, n of lambda, to be the norm of that operator, considering only values going up to lambda. Okay. And there's a couple of assumptions that we end up needing to make, and they're kind of all more notational assumptions, except for the last one. And basically, first thing that we end up needing is we need to assume that the local Hilbert space dimension that we're taking a look at scales polynomially with the cutoff. So if we have a situation where the cutoff ends up growing, you could have a situation where the cutoff ends up growing slowly, but the spacing between the energy levels becomes smaller and smaller and smaller. So you could actually have an infinite number of levels inside a finite space, and that causes our proof technique to fall apart. So in order to be rigorous, we need to make it have a polynomial scaling. So fortunately, for the cases that like examples like this that we're looking at, it scales quadratically. So that's polynomial. So that's no problem. But theoretically, there are examples of cases that will have scalings that our results don't hold for. The next thing that we end up needing is we need that the expectation value of the local quantum number on each of these individual systems is a constant for it. And we need this because of the fact that as we end up taking the system to get bigger and bigger and bigger, if the amount of energy per site isn't a constant and starts diverging, then we run into these situations where we kind of asymptotically end up getting infinities coming back out of it, and things don't make too much sense. But if we can guarantee that the average local quantum number inside the ground state is a constant in this limit, or is at most a constant, I should say, then also our results hold. Okay, so those are some important caveats. Next caveat that we end up having is about the growth of local quantum numbers. And so in particular, what we need to have is we need to have this guarantee that the projection of the Hamiltonian onto kind of like the two parts that we're interested in, this W and this R part, which is kind of like the truncated and the untruncated space. If we take a look at the projection on this, we need to end up having it grow at most like chi times lambda plus 1 to the rth power for some constant r. And so this is actually a relatively generous form that we end up assuming, but we kind of need to end up assuming some form in order to be able to make some progress. So that's what we end up doing. And if we, our claim is that if all of these assumptions are met, then your unbounded Hamiltonian will end up satisfying the one-dimensional area law. Okay. So let me go through and sketch the proof. The proof itself is kind of complicated and it's got a lot of steps, but the proof sketch itself I don't think is all that hard. So let's go through that. So the first part of the problem is we need to understand really how truncation ends up impacting our solution, because again, what we're doing over here is we're doing something like the following. We're taking our local electric field, which could be unbounded, and we're putting in these cutoff values, and we need to be able to argue that doing so doesn't end up impacting the structure of the ground state significantly under the assumptions that we've made over here, obviously. Okay. And so to do that, basically, what we need to do is we need to understand how the tail probabilities end up behaving for the quantum system. Yeah.
Scott used what the electric field, like how you're representing the electric field in this model.
Okay.
Electric field, like harmonic oscillator system, or
Okay.
is it the possible number that?
So it's kind of like that. So it's a little bit different than how you would normally end up seeing like photon number in a system, because with a photon number, you know, what you have is you have something like a dagger acting on n would be equal to what? Square root n plus 1, I think. Okay. And, you know, if I got that right, don't tell the CS department. And if I got it wrong, don't tell the physics department. All right. So that's what we end up having for ordinary harmonic oscillators. But in this case, for electric fields, what we have is we would have something like this. And so it doesn't have an eigenvalue that ends up depending on the particular value. So our raising and lowering operators here don't have these square root factors that end up coming in. So it's analogous to it, but it's a little bit different in the way that it's technically formulated.
So your E doesn't depend on M at all?
This notion, okay, I guess I called it U on the other slides over here. So this would be the analog of the raising operator that we end up seeing in this case. No, it doesn't. However, the energy that we end up getting in this case will scale quadratically over here. This E value is really just like the number operator that we would end up seeing for photons. And that thing does scale quadratically, just like we expect for the energy of an electric field. Okay. And it's just, this is an idiosyncrasy of the way that the field is represented in the Schwinger model. It doesn't end up looking like a photonic system. And that actually turns out to be really useful. Yeah.
And so the truncation you're talking about, is it truncation in Fock space or in electric field coordinates, or?
This is, formally speaking, it's a truncation in electric field coordinates, but in this case, they're linearly related to each other. So because the spacing between all of them in Fock is one level apart, just like you would end up seeing, you know, for bosonic operators, then it ends up holding. The only difference is that the eigenvalue spacing is also 1 for these operators.
Question about the assumptions that you made. They were formulated in the mathematical way, but from the physics side, we usually try to justify truncations. We would say, okay, the energy scale, yeah, the tail is really, that lambda is way greater than u, and so do we see?
Yeah, well, this is basically what I'm trying to get at is the second key point, behind this is that what we want to be able to do is we want to be able to say, make an argument kind of like the following. If we have a low-lying state and we've got, let's imagine that I end up having a situation like this where I have, if I have energy increasing in both of these directions, then I kind of expect some kind of a distribution that will end up having sharp tails like this. So as I go to higher and higher energies, I expect to have lower and lower density like this. And so what we need to be able to do in order to be able to prove this cutoff is really be able to show that the area underneath these tails over here is small past a certain point. Okay, so that's what I'm alluding to for this the second part of the proof. Okay, so we put these arbitrary boundaries on the tails, and then we show, okay, no matter what, there's a small fraction of the wave function that's beyond that point, and that fraction is so small that it can't screw up our area law. All right. And so then the simplest way that we could end up doing this, and this is actually the way that I first approached the problem, was to use a Markov inequality in order to be able to bound it, which basically says that the probability of you being k times the mean for a positive random variable is at most 1/k. And but unfortunately, this didn't give us quite tight enough bounds. Fortunately, several of my co-authors, or soon to be co-authors at this point, had published this beautiful work by John Preskill that ended up showing exponentially tighter bounds than you can get with a naive application of the Markov inequality. And that's how these guys ended up on the paper. I was like, gosh, you've got this beautiful result. How about you come in and we merge this all together? And that's how that part of the puzzle ended up happening. And okay, so what their result basically did is it ended up giving, for cases of simulating dynamics and strictly simulating dynamics, they were able to show that for unbounded Hamiltonians, that you can, under reasonable assumptions about the mean energy, like we made previously, that it satisfies a tail bound like this, and that you can reasonably truncate the high energy pieces of the dynamics and nothing bad will happen. So the natural thing to think about is, well, if somebody's got a result like this, can it be coupled with a proof technique like this over here in order to be able to show that the error that we get by doing the same thing to the approximate ground state projectors doesn't end up becoming something terrible? Okay, and that's how the whole proof ends up coming together at a high level. And so what we do is at a high level, we end up kind of breaking our system up into different pieces. We end up saying, okay, well, let's construct a left piece and a right piece over here. And then we're going to have all of these individual sites in between that go from some distance S in between. So we can imagine truncating it at, site L on this side, and then site L plus S on that side. Okay, and then we've got all of this junk to the right and all of this junk to the left. And what we want to be able to do is we want to be able to show that extended effects from those junk regions on each side won't really matter too much for us. Okay, and so basically, in order for us to do this, what we need to do is we need to consider truncations onto the actual space in between. So basically, the idea is that what we would like to be able to do is we'd like to be able to focus on the truncation just in here. Okay, and this effective truncation that we're looking at over here is given by the following. It's given by projectors onto that truncated space in the middle, but we don't do anything to the left and the right region. And we want to show that nothing really bad happens when we end up doing that. Furthermore, we want to consider a restriction of the Hamiltonian onto this space that's formed by the projection. Now, I emphasize restriction because this is important. Since our technique falls apart if we've got degeneracies, we can't just look at the projected Hamiltonian, because the projected Hamiltonian will have a kernel. And that kernel will lead to a huge degenerate subspace that makes our analysis tough. So we want to do a restriction. And what we mean by a restriction is we take that kernel and we just toss it out and we don't even analyze it. And so we only analyze the Hamiltonian on the space of non-zero eigenvalues. Okay, so this ends up leading to effectively a truncated system that looks like this in the middle, with these two regions left and right on the outside that we're treating with ordinarily. And now basically what we want to do is we want to take a Hamiltonian that is a truncation now of the left and right boundary to the teeth level up here, which is formally dictated by this. So now we've considered the following. What we do is we take one site now in the middle, we truncate that to level lambda and truncate everything else to t. And we want to be able to show that by choosing t appropriately, then it won't matter at all either for that. Okay. And so then with these two truncations put together, we can end up proving the following kind of robustness results on the distance. And basically what we end up saying is that if we want to make sure that that our truncation error in terms of the size of the projection is at most some constant, delta divided by 18 for technical reasons over here, then the cutoff value that we end up needing ends up depending on the norm of the effective Hamiltonian that we're looking at divided by that value of delta that we end up seeing. So this ends up showing actually under those assumptions and using those truncation strategies, that by cutting off our space at a level that shrinks or that grows inversely with the uncertainty that we're looking at, or I guess inverse squarely with the uncertainty we're looking at in the worst case, then we're going to actually be able to accurately mimic the system. So this says that effectively we can always end up finding a good truncation for these systems under that assumption. And yeah, furthermore, this formally will end up giving a bound on the trace distance in terms of this delta 2, which is upper bounded by that delta. Okay. Now, what we want to do is we want to take a look at the quantum tail distribution bound that we end up getting from the T truncation. For this guy over here, we basically can just end up using the result that they proved with John Preskill earlier. So we use that tail truncation over here to end up showing that ends up falling off now exponentially with the truncation that we're looking at, which is really nice. It's much better than the other one. Okay. And now, basically, what we end up doing is we can end up putting them both together using a triangle inequality in order to be able to find a bound on the combined error from both of the truncations. And we end up finding, actually, in this particular case, that the distance delta 2 over here has some really nice properties. It scales linearly with the norm of the effective Hamiltonian that we're looking at. But interestingly enough, it actually ends up shrinking exponentially over here with this kind of effective distance that we end up having on top. And this ends up leading to the fact that delta 1 and delta 2 actually end up shrinking, of course, using the fact that delta 1 and delta 2 end up shrinking exponentially with the cutoff. What this ends up saying is that if we put all of this together, then actually we can end up getting into this situation where we can create a bigger and bigger cutoff and cause this to actually shrink extremely quickly. And so this ends up leading us naturally to the one-dimensional area laws. And so with this, what we end up needing is we end up needing the notion of a approximate ground state projector. Now, approximate ground state projector, it's kind of straightforward what it does. It projects onto the ground state approximately. Okay, so the idea basically behind an approximate ground state projector is, imagine you got the following, right? You've got, let's say for the sake of argument, we have some region where we want to know our ground state is going to be in. We know it's going to be near energy zero inside some window out here. What we'd like to do is we'd like to be able to build a projector that ends up kind of looking like this. Okay, and an approximate ground state projector is exactly something like this. Ideally, it would be a Heaviside function that would just step up and only project onto a given vector if it's inside that energy window. But technically, something like that requires an infinite series. It's hard to analyze. And so it's more natural to consider an approximate ground state projector, which would use a polynomial approximation to a Chebyshev to the step function over here. And actually, this is kind of interesting for those of you who have looked at the quantum singular value transformation, because the Chebyshev polynomials that you end up using in the quantum singular value transformation to do the same thing in quantum computing actually are the exact same things that they proposed in 2017 to use for these approximate ground state projectors. So it's really kind of interesting that the field reinvented this exact same idea in a different context later. But I guess anybody who's read Russian math knows that this happens all the time. So that's the basic idea. So what we would like to be able to do is we'd like to be able to build such an approximate ground state projector. And here's like a formal definition of what those mean, but we're probably running low on time, so I won't dwell on the definitions of it. What we do then is we end up showing that we can end up building a low order Chebyshev polynomial that will approximate this step function very accurately. Then we apply the Chebyshev polynomial of the acting on the Hamiltonian in order to be able to implement this projector. And then we can reason about what the probability is of failure as a function of the degree. And basically, it ends up going down exponentially with the degree that we're looking at. So Chebyshev polynomials do an awesome job of approximating these functions. And so just to give you an idea, like, you know, this is kind of how the approximation ends up going for the first like 80 Chebyshev polynomials, and they end up getting kind of like flatter and flatter out around here, and then fall off faster past a particular cutoff. And so that ends up giving us kind of the structure that we end up needing for that. So yeah, the next step that we end up doing is we end up saying, okay, well, let's take this approximate ground state projector, apply it to our to the system, and then argue about what the entanglement entropy is. We go through, we do some standard triangle inequality bounds on it, and then we end up actually showing that the amount of entanglement entropy that we end up getting is related to this constant R that we end up having for the ground state projector. And that value of R, we can end up relating to these properties of delta and the norm of the Hamiltonian. Going through all of this rot and using the results that we have from the 2017 paper, we end up getting the following sort of scaling. At R ends up going like the distance between the two regions times this constant L over here, where L is the degree of the polynomial that we're looking at. And from that result, when we plug it in, we end up seeing that the entanglement entropy of this individual cut scales logarithmically with this R value. And in order to be able to claim that it's a area law,
Wait, what is
that's the part that I'm kind of getting to. Or actually, let me just go back a little bit to the definition of the AGSP, because what it is it's a sigma R AGSP, and so R here is basically like the rank that we end up needing of our kind of operators that end up decomposing the projector in those two-dimensional spaces. And because the Chebyshev polynomials converge very quickly, we only need logarithmically many. So it scales logarithmically, but we still need to be able to say that it's actually better than logarithmic. We need to be able to say that it's a constant. Okay. And so the final piece over here is we need to place these bounds on R. And these bounds end up coming from this Vazirani paper of 2013. And we end up finding that basically from the use of these techniques, we can end up actually finding a particular AGSP that has a value equal to sigma of 1/2R. And then we end up coming to this conclusion that if this appropriate weighted sum is order 1, then the entanglement entropy is order R. But in order for this to end up applying, we end up needing that the this value R over here is small. Now, the value R that we're talking about can be shown to be order 1 if the mean energy of each of the local systems is order 1. And that is one of the reasons why we needed the mean energy previously in our assumptions to be order 1, because of the fact that that ends up actually giving us that R is order 1, and then in turn that we have a one-dimensional area law. So this is how the truncations end up coming together to do it. High level, again, the story behind it, there's a bunch of math that unfortunately I didn't have enough time to really go over in great detail. But the high level idea is that what we do is we take a look at our system, we break it up into different regions, we truncate the space in here, then we truncate the space out there, and consider a projection of everything onto the ground state using this approximate ground state projector technique. That way we can take a look at what the properties of the ground state actually are in an analytic way. This ends up giving us, in the end, scaling when we combine everything together, that is O1 for the entanglement entropy using this 2013 result on approximate ground state projectors. Okay. So that's the basic idea behind it. When we plug this in to things like the original Hamiltonian that I discussed previously, we get exactly a 1D area law being satisfied because of the fact that you can prove that the system ends up having a local expectation value that's order 1 for the electric field in its ground state. And so that says that that satisfies it, as do models such as the Hubbard-Holstein model, which is another kind of related model for boson-fermion interactions. So that ends up giving us how this whole thing works. So it just kind of to conclude, what this work ends up showing is that area laws actually do still end up applying even in situations where you have operators that are not acting on a Hilbert space, right? Because, you know, if you've got operators that are unbounded, more broadly speaking, they're actually on a rigged Hilbert space, which is a particular type of a Banach space. And we can't necessarily apply the same reasoning that we wanted. However, by applying a series of truncations to our system, we can end up showing that the error that we get by approximating these unbounded systems by bounded systems is not actually all that bad, even in the worst case scenario for a low energy system. And so this ends up implying in the end, because we can closely approximate, that this is that basically the 1D area law holds more broadly than anybody previously thought. The remaining question is, well, okay, it's kind of a shame in many ways that this proof technique, which we liberally rip off, works for degenerate ground states, but yet our arguments that we ended up using fall apart for the degenerate case. So I feel in my gut that given enough time, we ought to be able to make this proof apply for the case of degenerate ground states as well, but we haven't done it yet. The more interesting question, though, going back to Arthur's criticisms, is, well, can we extend these ideas to various families of two-dimensional systems? That would be really interesting because obviously, you know, we don't just live in a one-dimensional world. And it would be great to understand whether there exists wide families of systems that have local interactions that are unbounded and also do satisfy area laws, because that might help us understand what the limitations are for classical computers simulating electrodynamics in more than just one dimension. And in turn, from my perspective, also help us understand what the gulf is between the capabilities of quantum and classical computers, because many such systems that obey these area laws can be simulated easily on classical computers. And understanding this is an important step towards us getting a complete understanding of the power of computing. Thank you very much.